Hello everybody. So we are still talking about the equation of continuity, and we showed that this equation is satisfying two of the three conditions that we wanted to be satisfied in the equation or the general equation of diffusional mass transfer. And here we're going to continue and check if the third point is satisfied or not. But before we do that, we need to discuss this part quickly, which is related to the application of the continuity equation on the whole flow. So we mentioned previously that the equation of continuity can be applied for one species and for another species using the mass units and using the mole units, and we said that this is the general form of the equation. It can also be applied on the whole flow, so we can apply it to the whole flow by adding the equations of the continuity of each species separately, and this is what we do here. So here you see we have NA plus NB, and this is rho A plus rho B, and this is RA plus RB, and of course NA plus NB is the total flow or total flux, which is the rho A VA plus rho B VB, which is rho multiplied by V, and rho A plus rho B is the total density of the mixture. RA and RB are, so we have only two components, so the only possible reaction is that A goes to B or B goes to A. So this is the only possible reaction that might take place. And this is in any reaction, for this reaction or any other reaction, the conservation of mass must be satisfied. So there is no change in the mass, no matter what reaction it is, because the mass on the right hand side of the equation equals the mass on the left hand side. It can have different number of moles. It's not a big deal, but from the stoichiometry or the balance of the equation, you can have different number of moles on the right hand side than what you have on the left hand side, but the total mass that you have here must be equal to the total mass that you have here, because mass is conserved. So RA, which is the rate of production of A, and RB is the rate of production of B, they must be equal but negative, because the mass of A that is consumed is produced in B and vice versa. So this term RA plus RB must be zero for the total flow in the mass units, not in the moles units. It's not the case in moles units. In moles it's going to be just it's a special case, but for the mass units it must be satisfied, and that's why this term would be cancelled out, and we will end up with this form of the equation. This term can be expanded using the expansion rule that we mentioned in the previous video. So it's gonna be rho del dot V plus V del rho, and these two terms are the total derivative. We can put them together as the total derivative, and this is the reason I discussed the total derivative. I don't think we are gonna use it anymore, but this is just to mention this. So the equation is valid for the mass units, and it's valid also for the mole units. So we can do the same for the mole units. We have two or molar fluxes. We have two equations for the two components A and B, and if we add the two components, then the equation would be del dot CV, which corresponds to the rho V, like we have in the previous case, which is rho V here, and the CA plus CB equals total C. But here we cannot put RA plus RB equals to 0, because the number of moles is not very probably to be not the same. So we'll keep this as the general form of the equation. So this is how we can represent the equation in the units of mass, in the units of moles, for a single component, for a mixture, or for the whole component, or the all components in the mixture. And now we need to check the last point of the 3 points that we wanted to check in the new equation. And the last point is how to produce if the equation can produce the concentration gradient or the concentration profile or not. So from the continuity equation that we presented, we can see that the equation has three terms. These two terms, rho partial rho A partial T and RA, are both function of concentration. They are directly represented in the terms of concentration. The concentration is here, it's already here, and the R is, again, we said it depends on the kinetics of the reaction, but it must include a concentration term in it. So it is directly a function of concentration. So if for instance, if you have a first order reaction, then it's going to be K multiplied by C. So it's inside it there is a C. But for N, it's not that simple and not that straightforward. So for the mass flux or the mole flux, we know that they are dependent on the concentration, but they are not directly put in the form of concentration. So one thing that we can do is to for these terms in red, we can put the definition of the flux, and then see how the equation will look like, and then check if the equation now satisfies our last point or not. So we need just to go back to this table. This is the table that we showed in chapter 22, the first chapter in mass transfer at the textbook, and we showed that there are 8 forms of the equation depending on the mass or mole, or depending on the concentration and density if they're constant or not, and depending on if I am measuring the flux relative to stationary axis or the average velocity. In our case, this is something that is dependent on the derivation that we made, and that's why it was necessary to do the derivation from the very beginning and to go to the steps one by one, because this is something that we need to choose based on this definition. We put this balance equations, or we applied the balance equations on this cube in the space. So this cube has the dimensions delta x, delta y, and delta z, and we did the balance equations so that we check the mass in and mass out, and mass in was at point z, and the mass out was at point z plus delta z. This point z is defined with reference to the origin, the point of x equals 0, y equals 0, and z equals 0. So it is relative to a stationary point, or stationary axis. It's not relative to the average velocity. And this is important, because in this case I know that I should pick something from this column. These equations are not gonna be useful for me at all. They do not represent the flux that I have been describing in the derivation. So this is one important point that I want to pick. And now then I have to choose a form of the flux from out of 4 instead of 8, so this makes the choice easier. And now I have 2 cases for mass flux and 2 cases for mole flux. So if I'm working with or using the equation using the molar units, then I should pick one of these 2, and for the mass units I should pick one of these 2. So what I would do is I would go for the most general form of the equation. The special cases are special cases of the general form of the equation. So I would go for the general form. If I'm using or doing the calculations on a special case, then the equation would go to the special form of the equation. So I would go for this form and this form, depending on I'm currently on mass units, so I'm going to pick this form of the equation. So what I'm going to do now is I will take this definition or form of the flux units. So this is what I have, but I wanted to put it in the form of rho instead of n. So I would have mass concentration and mass fractions instead of having fluxes. So I replaced this term, which is omega a multiplied by Na plus Nb. I replaced it with the rho a multiplied by b. So to know how this went from here to there, we need to check what these terms represent. So omega a is the mass of A divided by the total mass, which is the mass fraction, and Na plus Nb is the total flux, which is the total mass divided by area divided by time. So if I multiply these two, then it's going to be the mass of A divided by area divided by time. At the same time, if I multiply the mass concentration, which is mass of A divided by volume, if I multiply this by the velocity, it's going to give me the mass flux as well. So that's why this term equals this term. So this is the mass of A per unit area per unit time. So this, if I substitute with this form of the equation in the continuity equation, then I will end up with this. I can expand this bracket by applying the del on this term and the del on the second term. So this is how the equation will look like in the mass units. And for the molar units, it's going to be like this. I would like to take few seconds to talk about this. So this is now the continuity equation in the term of the mass concentrations and the mass fractions. And I would want to think if this is now satisfying what we were looking for or not. So this is a differential equation. So the way we solve a differential equation is by integration. So if I am able to integrate this equation, then the this is the del of del omega A. So this is the second derivative of omega A with respect to x, y, and z, and this is the second derivative of ya with respect to x, y, and z. So if I'm able to integrate it once, then the output of the solution of this equation is going to be the gradient of omega A. So this is the derivative of the gradient. So if I integrate it, it's going to give me the gradient. So now this equation is giving me the chance to have the gradient of the concentration profile, the mole fraction profile, the mass fraction profile as an output of the solution of the equation. It's not like fixed first law. For fixed first law, we were using this as an input so that we can calculate the flux, but in this case this is an output of the equation. So now I am able to use this equation or to solve this equation and produce the concentration profile, which is what we are looking for or we're trying to achieve from the beginning. So now this last term here is now satisfied, and this equation has a term that allows to predict or produce the concentration at any point within the diffusion distance. So this is like an important thing to know, that the equation is satisfying all our requirements and it can be used to do all what we need to do. So this is the point that we wanted to highlight in this video, the main point. In the next video, we will show we'll talk about some special cases of the continuity equation and see how these special cases would simplify the solution for us. So I'll see you in the next video, inshallah. Assalamu alaikum.